Okay, so let's get started. Welcome everyone. Thank you for joining us. This is online Spintronic seminar number 115. The speaker today is Professor Dingfu Shao from the Institute of Solid-State Physics of the Chinese Academy of Sciences. His talk will be about spin-neutral currents for antiferromagnetic spintronics. Professor Shao received his bachelor's degree from China University of Mining and Technology in 2008 and a PhD from the University of Chinese Academy of Sciences in 2013. He was a research assistant professor at the Institute of Solid-State Physics of CAS from 2013 to 2016. And then he was at the University of Nebraska-Lincoln as a postdoc from 2016 to 2021, working with infinite symbol. In 2022, he joined the Institute of Solid-State Physics as a professor. His research is focused on exploring the fundamental properties of quantum materials using first principles calculations and model approaches. His recent interests include the symmetry-related transport properties in anti-ferromagnetic and two-dimensional ferroelectric materials and their applications in electronic and spintronic devices. So as I mentioned, his talk will be about spin-neutral currents for antiferromagnetic spintronics. And please take it over from here, Dingfu.
Okay. So, can you see it? Okay, thank you, Kirill, for this nice introduction. Hello, everyone. My name is Dingfu Shao. I'm from Institute of Solid-State Physics, Chinese Academy of Sciences. First, I want to thank Kirill and Xin for organizing this wonderful seminar and thank their kind invitation. And it's my pleasure to have a chance to here to share our recent work on antiferromagnetic spintronics. We know in spintronics, the spin polarized currents play a central role, while the spin neutral currents are usually considered to be useless. We found recently, in contrast to this common expectation, the spin neutral currents can be very useful, especially for antiferromagnetic spintronics. Today, I will show you some typical examples. Well, in spintronics, the most investigated materials are ferromagnets. That is because the ferromagnets has a large magnetization, very easy to control and detect. Although nowadays the spintronic devices based on ferromagnets have been widely used in information technology, there are still a lot of shortages for ferromagnets. First, for example, its dynamics is about gigahertz, indicating the operation speed is not very fast. And it has a large magnetization, very easy to be disturbed by a magnetic field, which will influence its stability. And the large magnetization also generates a sizable strip field, which will influence the adjacent device units. In order to overcome this problem, we have to move this device units far away from each other, which is not good for the high density applications. On the other hand, antiferromagnets do not have these problems. The dynamics is about terahertz, indicating our ultra-fast speed. And the zero magnetization make antiferromagnets very robust against the magnetic field. And the zero magnetization also indicating the absence of strip field, so that we can put the device units close to each other, which is wonderful for the high density applications. So antiferromagnets is are very suitable for the spintronic applications with high speed, high stability, and high density. All these are very promising. However, the antiferromagnetic order parameter, the so-called Néel vector, is very difficult to control and detect, which restrict the realistic application of antiferromagnetic spintronics. And this is largely due to the absence of spin polarized currents in the antiferromagnets we usually considered. And in the recent years, researchers have made extensive efforts to find efficient methods to control and detect the Néel vector. For example, we can find some antiferromagnets with a strong magnetoelectric coupling and use the electric field to switch the Néel vector. We can also deposit the antiferromagnets on the top of some piezoelectric substrate and using string to switch the easy access of the antiferromagnets. A recent hot topic is using the spin orbital effects such as the Rashba-Steen effect or the spin Hall effect to generate the spin orbital torque on the antiferromagnets to realize the reorientation of the Néel vector. Although we have this very less progress to control the Néel vector, the Néel vector detection is still very challenging. So far, the most common method to detect the Néel vector in compensated antiferromagnets are the anisotropic magnetoresistance and the spin Hall magnetoresistance. These effects are driven by spin neutral current, and the signal of these effects are usually very weak. It will be promising if we can introduce the anomalous Hall effect in antiferromagnets for the Néel vector detection. However, the antiferromagnets supporting the anomalous Hall effect are in fact the uncompensated antiferromagnets, which means they should have ferromagnetic symmetry. So the non-vanishing, tiny but non-vanishing net magnetization and the anomalous Hall effect and the spin polarized currents are largely supported by symmetry. However, in order to realize the efficient Néel vector detection and manipulation in perfectly compensated antiferromagnets, we still need to explore more Néel effects and material platforms. Recently, I have been working on this field and predicted some very phase-related properties used for Néel vector detection. For example, we found in some antiferromagnetic metals near the Fermi level, there might be a direct nodal line protected by a symmetry. The Néel vector rotation can control this symmetry and leading to the gap opening and the closing, the switching the gap opening and the gap closing states along this direct nodal line. And this will generate a sizable change of the spin Hall effect. And we also found in some non-central symmetric antiferromagnets, we can have a Néel vector dependent nonlinear anomalous Hall effect. These effects are very interesting, and because there are strong response against the Néel vector rotation, we can use these effects to detect the Néel vector in this compensated antiferromagnets. However, these effects, together with the anomalous Hall effect and anisotropic magnetoresistance effect I mentioned in previous page, are all associated with the spin orbital coupling of antiferromagnets itself. It would be promising if we can make use of the much stronger exchange interaction of antiferromagnets. We may expect much stronger spin-dependent transport property for large on and off ratio and efficient manipulation. For example, in conventional magnetic tunnel junction based on the ferromagnetic electrodes, we can have a giant TMR for information readout, and we can have STT for information write-in. It would be desirable if we can have a similar antiferromagnetic tunnel junction and using these methods for readout and write-in. However, the conventional understanding tells us these effects are all based on the spin polarized currents, where the spin polarization P is finite. While in antiferromagnets, we usually have only a spin neutral current where P is 0. So it seems it's impossible to have a realistic antiferromagnetic tunnel junction with these effects. Recently, we found this is not true. In fact, we can have antiferromagnetic tidal junction useful with the spin neutral currents. In such antiferromagnetic tidal junctions, the spin neutral currents can drive TMR and the tunneling anomalous Hall effect and the spin transfer torque. I will first discuss the TMR. Although in conventional magnetic tidal junction, the TMR is usually understood by the control of the tunneling of the spin polarized currents by the relative direction of the magnetization of the two electrodes. Here we consider this simple magnetic tidal junction where the two electrodes are identical. So in the magnetization of if the magnetization of the two electrodes are parallel, the density of states for the two electrodes are the same. So the tunneling is allowed. We will have a low resistance states. But for the anti-parallel state, the spin splitting in the density of states are opposite for the density for the two electrodes. So some electrons started from here. Wanted to land in here, but they will find there are no enough states for there to occupy. So the tunneling will be blocked. We will have a high resistance state. This picture can be understood by this empirical model where P is the spin polarization of the current within each electrode. P is usually defined according to the density of states. Obviously, the larger P with the larger TMR we should expect. And well, for antiferromagnets, because we usually have the spin degenerate density of states, so P is obviously 0 according to this definition. So according to this model, it seems it's very difficult to realize TMR in antiferromagnetic tidal junction. We find that this picture may not be accurate because the density of states is the average property of the materials and cannot reflect a specific transport property along a specific direction. Here we want to consider a more accurate picture. So we consider we have a ferromagnetic metal where in its Brownian zone. We have a spin up Fermi surface here and the spin down Fermi surface here. And because the values of the spin up and the spin down Fermi surfaces are not the same, so if we apply our electric field, we will naturally generate a spin polarized current. And then we consider we have a bonistic transport, which means we do not have any scattering. So if we have two identical electrodes using such a ferromagnets, and during the tunneling, because we do not have a scattering, the tunneling is completely determined by matching of the Fermi surface of the two electrodes. So in the parallel state, for the two electrodes, the spins are the same on the Fermi surface. The tunneling is allowed. We will have a low resistance state. And for the anti-parallel state, the spins on the Fermi surface are opposite for the two electrodes. So we'll have the tunneling is blocked. We will have a high resistance state. Next, we can consider a different situation where the spin up and the spin down Fermi surface have a similar value. In this case, we will have a nearly spin neutral current, but we can still have a low resistance state and a high resistance state by matching the Fermi surface of the two electrodes. So obviously, if we can find an antiferromagnetic metal with such a non-spin degenerate Fermi surface, and we can use this antiferromagnets as an electrode to build the tidal junction and get the TMR by matching the Fermi surfaces. But previously, it seems by default, people can consider antiferromagnets can only have a spin degenerate band structure. That is because antiferromagnets usually have some symmetry operations such as immersion plus time reversal, where without spin orbital coupling, we can have the spin rotation plus translation. This symmetry operations enforces zero net magnetization, also enforce the Kramers spin degeneracy everywhere. So obviously, if we can break these two symmetry operations, we can have the non-spin degenerate band structure. And even without these two symmetry operation, we can still have a zero net magnetization with the help of some crystal symmetries. For example, here I show our glide mirror symmetry Gx and glide GZ. Gx can preserve the X component of net moments, but flips My and Mz. And the GZ will preserve Mz, but flip Mx and My. So if we combine these two symmetry operations, we will get the net magnetization. We found that recently discovered high temperature antiferromagnetic metal, ruthenium oxide, it has such a property. It has a titanium oxide type rutile structure, and the Néel temperature is over 300 Kelvin. The Néel vector is a non-one direction. In its magnetic space group, it doesn't have this symmetry, but have two glide and one mirror. These symmetries will these symmetry operations will enforce the zero net magnetization. So ruthenium oxide is perfectly compensated. And these symmetries allow the sizable spin splitting in the band structure along this direction, which will generate the non-spin degenerate Fermi surfaces. If we consider a transporter along O1 direction, we can project these Fermi surfaces into the 2D Brownian zone and get the numbers of the conduction channels contributed from these Fermi surfaces. We can further calculate the spin polarization of these conduction channels. Obviously, the total spin polarization of all the conduction channels must be zero because the spins are anti-symmetric with some glide or mirror symmetries. But locally, most of the conduction channels are fully spin polarized. So if we use ruthenium oxide as the electrodes to construct the antiferromagnetic parallel junction, in the parallel state, the conduction channels for the two electrodes will have the same spin polarization. So the tunneling is allowed, we will have a low resistance state. But for the anti-parallel state, the spin operations for the conduction channels in the same K parallel will be opposite. So the tunneling is blocked. We will have a high resistance state. Therefore, we should expect the J and the TMR. In order to demonstrate this, we use ruthenium oxide as an electrode and the titanium oxide as a barrier to construct such an antiferromagnetic parallel junction and performed the quantum transport calculation. We found in the parallel state in the 2D Brownian zone, the error with high transmission is consistent with the distribution of the conduction channels of bulk ruthenium oxide. But for anti-parallel state, only the error with small spin polarization contribute to the transmission. And this is the clear evidence of the matching of the matching of the conduction matching of the conduction channels of the two electrodes. And if we integrate all the transmission of the momentum in the 2D Brownian zone, we can get the total transmission. We find that the total transmission is always large for the parallel state compared to that for the anti-parallel state, which leads to a positive TMR in the calculated energy window. The minimum TMR is here over 50%, and at the Fermi level, we got the J and the TMR over 500%. This value is already comparable to the commercial ferromagnetic parallel junction and clearly proves the advantages using TMR to detect the Néel vector for antiferromagnetic spintronics, even though in this case we have only the spin neutral currents. We can further analyze the spin polarization of the conduction channels If we consider the transport direction along z direction, if the electrode have a mirror symmetry perpendicular to z, the conduction channels then can only have the z spin polarization. But if we can have a time reversal plus a twofold rotation around z direction, the conduction channels can have only the in-plane spin polarization. But if we do not have these two symmetry operations, the conduction channels can have all the spin components. These symmetry arguments works not only for the collinear antiferromagnets, but also for other type magnetic materials. For example, in some non-collinear antiferromagnetic metal, the anisotropic spin texture on the Fermi surface will contribute to the non-collinear spin polarization on the conduction channels. So using such a non-collinear antiferromagnets as an electrode to build a Taylor junction, we can get a TMR by matching these conduction channels. This mechanism of matching conduction channels have recently confirmed by two experiments. These two groups use the non-collinear antiferromagnetic metals, manganese platinum or manganese tin, as the electrodes to build the Taylor junction. And by matching the conduction channels, they got the sizable TMR. But the matching of the conduction channel is not the whole story. We still need to consider the barrier, because the matching of the conduction channel is through the no decay rate evanescent state in the tunneling barrier. For example, here we have well spin polarized conduction channels here. But if the barrier, if in the barrier the no decay rate is located here, the overlap between the conduction channels and the no decay rate error is very small. In this case, the transmission for parallel state and the anti-parallel state do not have a big difference. So we can only have a small TMR. But if the overlap is very large, we can expect a very large TMR. So for example, we have such non-collinear antiferromagnetic metal, manganese gallium nitride, which has the well spin split Fermi surfaces. If we integrate the spins on the Fermi surface along z direction, we can get the distribution of the spins on the conduction channels in the 2D Brownian zone. We find that this distribution have a cross pattern. This reminds us in the widely used barrier material STO, the no decay rate error also has a cross pattern. So we use manganese gallium nitride as an electrode and STO as a tunneling barrier to construct a non-collinear antiferromagnetic Taylor junction and perform the quantum transport calculation. We find in the parallel state, in this cross error, we will have a very high transmission. But in the antiparallel state, in this cross pattern, cross error, the transmission is significantly reduced. This generates an ultra large TMR over 10 to the power 4% at the Fermi level. So clearly, by matching electrodes and the barrier, we can enhance the TMR, which will be very promising to realize a readout with a large on-and-off ratio for antiferromagnetic spintronics. Next, I will show you by matching of the electrodes and the tunneling barrier, we can have some other interesting properties, such as a tunneling anomalous Hall effect. We know the Hall effect is the effect that we apply a longitudinal current in a material under a magnetic field and generate a transverse Hall current. And if we can generate the transverse Hall current spontaneously without a magnetic field, then this is an anomalous Hall effect. Anomalous Hall effect is an intrinsic property of ferromagnetic metal, and the Hall current direction is strongly dependent to the magnetization direction. So this effect is widely used to detect the ferromagnetic order parameter. The anomalous Hall effect can be introduced by intrinsically by barrier curvature or extrinsically by some impurity scattering. These mechanisms will generate the transverse velocity to the electrons. According to this simple picture, we found these arrows are the spins of the electrons. Also, according to these pictures, we can clearly see the spins with the opposite, the electrons with opposite spins can get the opposite transverse velocity. So if we have only a spin neutral current where the numbers of spin up and spin down electrons are the same, we will not have a net transverse velocity to generate a finite anomalous Hall effect. Only if we can have a longitudinal spin polarized currents where the numbers of spin up and spin down electrons are not equal, we can have a net transverse velocity for a finite anomalous Hall current. And in this case, we can see the driven current is spin polarized. The output Hall current is also spin polarized. Recently, people found the anomalous Hall effect can not only emerge in bulk metal, but also emerge in TAHE junction, where the left ferromagnetic electrode and the right normal metal electrode are separated by a tunneling barrier with a strong spin orbital splitting. This effect is called tunneling anomalous Hall effect, and its mechanism is the momentum-dependent spin filtering. Here we describe this mechanism by using this simple TAHE junction, where the left electrodes and the right electrodes are very simple normal metal, but the barrier we choose the tin telluride type insulator. Tin telluride is a two-dimensional ferroelectric material with in-plane ferroelectric polarization. It has a glide mirror perpendicular to Z direction, enforcing the Eastern type spin orbit coupling, which means in its non-spin degenerate band structure, we can only have the Z component of spins, but we do not have X and Y components of spins. This means the spins is still a good quantum number in this TAHE junction, which largely simplified our analysis. So we know within a current, the electrons can have different velocity directions. So in each velocity direction, the numbers of spin up and spin down electrons are equal before in the left electrons. During the tunneling, because in the barrier we have a very strong Eastern type spin orbital coupling, the tunneling barrier height for spin up and spin down electrons are different. We can then use the tunneling barrier height to define a spin filtering factor F. For a positive F here, we basically have the tunneling of a spin up electrons and the spin down electrons are majorly filtered out. For a negative F here, the transmission is majorly contributed by the spin down electrons. As a result, after tunneling, we found the spin up half of electrons are filtered out, and for the remaining electrons, the spin up electrons are majorly have the positive transverse velocity, and the spin down electrons have majorly the negative transverse velocity. This generates a net transverse spin current. This effect is called tunneling spin Hall effect. Here, we only show the distribution of the spin filtering factor F along kx direction, but in tin telluride, the distribution of the F in 2D Brilliant zone should look like this. Next, we change the left electrode to a ferromagnetic metal, where the Fermi surface is well spin polarized. In this case, longitudinal currents will carry mostly spin up electrons. We find in this case, the tunneling in this area is allowed, and in this area is largely blocked. This will generate an additional charge Hall current in this direction. So this effect is called tunneling anomalous Hall effect. Because tunneling spin Hall current and the tunneling anomalous Hall currents are parallel to each other, we can say the tunneling anomalous Hall current is spin polarized. which means in this effect, both the driven and the output Hall currents are spin polarized, which is consistent with the common expectation of the anomalous Hall effect. If we consider red electrode it has a free electron model, we can write down the formula to calculate the longitudinal conductance and the thalonium anomalous Hall conductance and the thalonium spin Hall conductance. Here, the T is a momentum dependent transmission, and the P is the spin polarization of the transmission. So obviously, according to these two formula, if we have some unbalanced distribution of a T or PT, we may expect large thalonium spin Hall effect or thalonium anomalous Hall effect. Next, we change the left electrode to a ruthenium oxide type antiferromagnetic metal. As we mentioned previously, ruthenium oxide can support the spin neutral currents with momentum dependent spin polarization for the electrons. So we can match the conductive channel of ruthenium oxide and the distribution of the spin filtering factor in the barrier to find out how the distribution, what is the distribution of the transmission. We find that in the top half, the spins are matched for the barrier and the electrode. Then we have a large transmission. But for the bottom half, the mismatch of the spin polarization for the barrier and the electrodes leads to a small transmission. This generates unbalance of the transmission along y direction, which will result in a large anomalous Hall current. But if we consider spin, we find in the left half, we have mostly spin down electrons. In the right half, we have mostly spin up electrons, which generates a spin Hall current along x direction. So in this case, the thalonium anomalous Hall current and the thalonium spin Hall current are perpendicular to each other, which means the thalonium anomalous Hall effect, thalonium anomalous Hall current is purely spin neutral. So we have both driven current and output Hall currents spin neutral, which is completely different to the conventional expectation of the anomalous Hall effect, where both driven and output currents are spin polarized. In order to demonstrate this, we consider the thalloid junction where the components have these Hamiltonians. Here, the J is a parameter to describe the spin splitting in the band structure of the ruthenium oxide, and the alpha is a parameter to describe the Eason type spin orbital coupling in the barrier. The right electrode has a free electrode model. So we find if J is 0, which means no magnetism, or alpha is 0, which means no spin orbital coupling, the transmission patterns are highly symmetric, leading to a 0 anomalous Hall effect, 0 thalonium anomalous Hall effect. So next, we can increase J and alpha to see what can happen. I don't know if you have such experience during our research. We sometimes may have may got some totally unexpected results, which can give us incredible prayer. Here, when I increase J and alpha, I got the most surprising figure in my career. When I first saw this perfect heart-shaped figure, I was extremely delighted. I think this implies what I'm doing is very romantic, and I believe I will repeat telling this story in the future, because this is a wonderful example to show people the physics is interesting, the spintronics is interesting. And also this transmission pattern, we can see we have a very strong unbalanced distribution along y direction, which generate a large thalonium anomalous Hall effect with a Hall angle about 4% in the right electrode. This value can be comparable to the Hall angle in the conventional ferromagnetic bulk metals. And if we consider a spin polarization of the transmission, we find the spins are anti-symmetric along x direction. which will generate sizable tunneling spin Hall effect along X direction. We find that these two effects can also emerge in left electrode, and the Hall angles can be even larger. Since the switching of the Néel vector will also switch the spins on the Fermi surface for ruthenium oxide, in order to simulate this, we change J from positive to negative and find the tunneling anomalous Hall effect is an odd function of J, which means we can use the tunneling anomalous Hall effect to detect the Néel vector. And since tin telluride is a ferroelectric material, the switching of ferroelectric polarization can switch the spin texture on the barrier. So we change alpha from positive to negative, and found that both effects are odd function of the alpha, which means we can use the ferroelectric switching to control these effects. This will open new opportunities to design the voltage controlled spintronic devices. So using these two examples, we prove even with only the spin neutral currents, we can have the sizable spin dependent transport property in antiferromagnetic tunnel junction with large on and off ratio. But in order to use this antiferromagnetic tunnel junction in practice, we still need to find an electric method to control the Néel vector to realize the information right in. Let's first see the dynamics of the antiferromagnets. Here is the LLG equation of the one sublattice of collinear antiferromagnets. Here we have an effective field, which includes the anisotropic field and the external field and the exchange field. The exchange field is due to the exchange coupling of the two moments and two sublattices, and it can generate exchange torque M cross exchange field. Obviously, if the two moments are perfectly anti-parallel to each other, this exchange torque must be zero. But if we can find some perturbation to generate a canting, this cross product will not be zero anymore, so that we can have a staggered exchange torques for these two magnetic sublattices. Since in antiferromagnets, the exchange field is usually very large, this staggered exchange torque can drive the ultrafast rotation of the two moments. Obviously, in order to realize the switching of the Néel vector, we need to find a method to generate such canting. In principle, we can use STT to generate this canting. However, in the antiferromagnetic tunnel junction we considered, we have only the spin neutral current where the spin polarization P is zero. So it seems we cannot generate such STT. But consider in the conventional magnetic tunnel junction, if we have a giant TMR, we usually will also have the sizable STT. And since we have just demonstrated in antiferromagnetic tunnel junction, we can also have a giant TMR. Then I believe the STT can be realized as well. But the matching conduction channel mechanism cannot give me the answer of this question. So in order to solve this puzzle, I decided to check the local transport property of antiferromagnets. Here, I consider a very simple antiferromagnetic metal with only two magnetic atoms, A and B. A and B are with the same elements, but the moments of them are antiparallel. So if we apply our electric field to this antiferromagnetic metal, the generated longitudinal current can be decomposed into the intra-sublattice current JAA and JBB, or inter-sublattice current JAB. Since the atoms within the same sublattice will have same spin splitting on the density of states, the JAA and the JBB must be spin polarized, and we should expect their spin polarization are opposite. But the atoms for different sublattices will have the opposite exchange splitting on the density of states. So JAB should be usually spin neutral. The strengths of these currents are determined by the hopping between the atoms. So if we have such antiferromagnets where the intra-sublattice distance AA and BB are very large, and the inter-sublattice distance AB is very small, which means the hopping between AB is very strong, and the AA and the BB hopping is very weak. So in this case, JAB is much stronger than JA and JBB. We can simply consider these antiferromagnets as two antiparallel allied ferromagnetic sublattices connected in series. In this case, the longitudinal currents are majorly contributed as a spin neutral JAB. But if we can have such antiferromagnets where the AA and the BB distance are small, but the AB distance are large. In this case, the JA and the JBB are much larger than JAB. We can then simply consider these antiferromagnets as two ferromagnetic sublattices connected in parallel. In this case, even we have only the globally spin neutral current, but within the sublattices, we can have a staggered spin currents. We dub this staggered sublattice resolved spin currents as a Néel spin currents. So if we can find some antiferromagnetic metal supporting the Néel spin currents, we can use them to as an electrode to construct the antiferromagnetic halojunction. In this case, we can simply consider the antiferromagnetic halojunction as two ferromagnetic halojunctions connected in parallel. Therefore, the TMR and the STT are straightforward. And if the Néel spin current is followed across the barrier to the right electrode, it can generate the staggered spin polarization on the two sublattices, which means in the LIG equation, the M1 and M2 for the two sublattices are opposite, and the generated spin polarization P1 and P2 for the two sublattices are also opposite. In this case, the damping network M cross P for the two sublattices are staggered, which will not influence the perfect anti-parallel state for the two moments. But the field-like torques for M cross P for the two sublattices are parallel to each other. This parallel field-like torque can generate the canting of the two moments, and then the exchange torque can drive the ultra-fast rotation of the Néel vector. And when the moments are rotated parallel to the spin polarization P, this field-like torque will be vanishing. Then the rotation will stop, where we can then have the deterministic switching of the Néel vector, like I showed here. So in order to demonstrate this, I first calculate the spin polarization. I could first calculate ruthenium oxide and found the ruthenium oxide have very strong Néel spin currents, where the spin polarization is about 35%. This value is comparable to that in spin currents in the conventional ferromagnetic metal, iron, cobalt, and nickel. And then we use the ruthenium oxide as the electrode and the titanium oxide as the barrier to build such a halojunction and calculate the STT in the red electrode generated by the tunneling of the Néel spin current. We found that the STT are large at the interface, then become small, which is consistent with the case for a conventional ferromagnetic halojunction, indicating the tunneling spin currents are majorly absorbed by the interfacial atoms. And we found for the two interfacial layers, the field networks are parallel to each other, and the damping networks are anti-parallel. This proves the tunneling of the Néel spin current indeed transfers a staggered spin polarization to the red electrode. And we found that even we have some uncompensated magnetic moment at the interface, which may generate additional spin current and enhance the damping network if the belt voltage is large. The total field network is always dominant, which can be used to generate the deterministic switching. The demonstration of the Néel spin currents make us reconsider the mechanism of the TMR in antiferromagnetic tunnel junction. Previously, we considered in order to have a TMR in antiferromagnetic tunnel junction, the electrodes must have well spin polarized conduction channels. This means we can never use the antiferromagnets with spin degenerate film surfaces as an electrode in these tunnel junctions, because in this case, it only supports the spin neutral conduction channels. So in parallel and anti-parallel states, the conduction channels will always match, and we cannot generate a difference of transmission. But the demonstration of the Néel spin currents may make us recognize that we are in fact matching the sublattice resolved conduction channels with the help of the Néel spin currents. In this case, we can also use the antiferromagnets with spin degenerate film surface if they support the Néel spin current. Because the sublattice resolved film surface or conduction channels in these antiferromagnetic metals can be also well spin polarized. So we with the help of the Néel spin currents, we can match in this sublattice resolved conduction channels and get sizable TMR. In order to demonstrate this, we check the 2D antiferromagnetic metal iron 4 germanium telluride. Although iron 3 germanium telluride is widely investigated, but recently people found that there can be iron 4 germanium telluride, which can be A-type antiferromagnets by cobalt doping. The low temperature is about 200 Kelvin. This is the only two-dimensional antiferromagnetic metal I know so far. And because the weak interlayered coupling, we can naturally consider iron 4 germanium telluride as the ferromagnetic layers connected in parallel, which will naturally support a very strong Néel spin current. Using such a material as an electrode, we built some artificial implant tunnel junction and calculate the PMR and STT. We found that even with a PD symmetry in the bulk iron 4 germanium telluride and the spin degeneracy in the band structure everywhere, we can still have a sizable TMR and STT. This phenomenon cannot be understood by conventional mechanism, but can be well explained using Néel spin currents in this intuitive parallel connection model. In the end, I want to discuss the experimental opportunities. Since ruthenium oxide and titanium oxide are very easy to grow, we can expect high quality epitaxial antiferromagnetic tunnel junction using these materials to observe the TMR and STT driven by Néel spin currents. And for the tunneling anomalous Hall effect, the barrier material we propose, the tin tellurides, although it cannot be exfoliated from the bulk material, it can be grown on graphene. So we can put graphene on the top of ruthenium oxide and then grow tin telluride on the top of it. Or we can first grow tin telluride and then transfer it on the top of ruthenium oxide. Moreover, the monolayer HFAs MX2 materials such as MOS2 and WSE2 also have Eason type spin orbital coupling. So this material can be also used as a tunneling barrier to observe the tunneling anomalous Hall effect. And in this talk, we discussed the STT in the antiferromagnetic tunnel junction with two antiferromagnetic electrode layer. But in fact, we can generate a net self-torque in our device with a single antiferromagnetic layer. if the antiferromagnets have a symmetric top and bottom termination. And from the structure, we found many antiferromagnets have a small a distance, such as the manganese or chromium-based perovskites or widely investigated chromium iodide. Most of these materials may be insulating, so it will maybe be difficult to use the electric field to generate the Néel spin currents. On the other hand, we can use a temperature gradient or laser to generate the thermoelectric or photon-galvanic Néel spin currents, which may introduce the interesting functionalities. Finally, the Néel spin currents may bring new opportunities to these two-dimensional antiferromagnets. For example, we can put A-type two-dimensional antiferromagnets on the top of non-magnetic material, such as graphene. Then, if we apply an in-plane electric field, the Néel spin currents in the bottom layer of the A-type antiferromagnets can be injected into graphene and then detected by a ferromagnetic detector. This separating of the Néel spin currents may generate new opportunities for 2D spintronics using the antiferromagnetic material. In conclusion, previously, we usually consider only the spin polarized currents can generate the spin-dependent transport property used for information read in and read out for spintronics. But we found, in contrast, this common expectation that spin-neutral currents can be very useful, especially for antiferromagnetic spintronics. We can use it to drive the thalonium magnetoresistance, thalonium anomalous Hall effect, and the spin transfer torques in antiferromagnetic junctions. Previously, we consider this is due to the antiferromagnetic electrodes we choose have the non-spin degenerate film surface. But then we will recognize that is due to the spin neutral currents in antiferromagnets can host the Néel spin currents. Our work offers a very straightforward theoretical framework to realize all electric antiferromagnetic junction and may open new opportunities for antiferromagnetic spintronics. And we hope our work can stimulate the more exploration for the more interesting properties driven by spin neutral currents. Finally, I want to thank my collaborators. The major theoretical collaborators of the works I discussed today includes Professor Evgeny Symbol from University of Nebraska-Lincoln, Professor Shuhui Zhang from Beijing University of Chemical Technology, Dr. Gaotan Guo from Oxford, and my student Yuan Jiang, Professor Jun Ding from Henan University of Engineering. And I also want to thank these collaborators for helpful discussions. Some of this work are supported by these findings, and this is what I want to share today. And thank you very much for your attention.
Thank you very much, Ding Fu, for this very interesting talk. Let's use the reactions buttons to thank him for his presentation. The talk is now open for questions, discussion. If you have a question, please raise your hand in Zoom. Or if you're watching on Twitch, you can type the question into the chat box. So are there any questions, please? Chen, please go ahead.
Oh, hi, Ding Fu. Thank you very much for the exciting talk. I have one question regarding experimental realization. I also have this question when you talk about the ruthenium oxide. How do people usually control the Néel order of the ruthenium oxide?
So far in the experimental reports, people do not do specific treatment to control the domains alignments or neo vector alignments, but they have been observed that we can have some LED spin current generated, which means we do not have a perfectly compensated domains. So I believe if we directly deposit the ruthenium oxide, we can have some LED effects I predicted. Maybe it is not strong. I generated some supplemental page here. So I think probably in order to realize a strong effect, probably we can first align the domains by deposit ruthenium oxide on the top of some ferromagnetic substrate using the exchange interfacial exchange coupling to first align the domains in the reference layer. Then we can use the STT to align the domains in the top layer. Or recently, there have been reports used. We can directly put a very thin layer of a ferromagnetic layer on the top of some antiferromagnets, and by magnetic field, we can directly switch the neo vector of antiferromagnets. This may the ultimate goal is to realize all electric switching and the readout, but probably in the initial preliminary research, we can looking for the help for the some ferromagnetic substrate or a cabin layer.
Thank you very much.
Thank you. So there's a question in chat from Alexei Kovalov. I'm going to read it for you. In fact, I had a similar question. So the question is, how will the spin neutral currents be affected by interfacial disorder? So in fact, remember, there were some studies quite a while ago for conventional antiferromagnets, and it was found that you can have TMR and torques for particular polar magnetic ordering, but if you have roughness, those tend to be destroyed. So I think this will be a concern here if the roughness tends to place different magnetic sublattices randomly against each other on the two sides of the barrier. You showed some cases where that doesn't seem to be the case, so maybe you can comment on that some more.
Yes. This is a very nice question, and in fact, we are working on using a model to do it, and we are still working. We hope we can have a result soon. But first, I want to show you some attempts to quantitatively answer this question. Well, for TMR and STT, we have tested a different termination. We found that the TMR is always positive. And if we consider the roughness at the interface, we'll average these effects because we always have this positive giant values, then by average, these effects will still be there. And for STT, we also consider different cycles of the barrier to get the different interfacial termination. And in this case, we found that we still have a sizable giant dominant field network. And we think this is quite straightforward because unlike the previous consideration of the STT and the TMR, as due to the some coupling of the interfacial moments for the staggered spin density in the bulk, we in fact have a sublattice resolved current, and then we can because the current is very strong, and we can indeed to divide this antiferromagnetic Taylor junction to the two ferromagnetic Taylor junction. So in this case, like showing here, changing the interface effect, changing the interfacial effect, which means in the top half we have a smaller barrier width, and in the bottom half we have a larger barrier width. But we can consider these two halves are connected in parallel, so this will not influence the total effects. And another attempts we have tried is during the non-Euclidean Brim Green's function calculation, we change the broadening in the Green's function to simulate the, for example, we increase the scattering. And we found that if even we use a very large broadening, like 1 EV or 0.1 EV, we still have a very strong effect. So I think this is quite straightforward, and at least for this case, I think it's very understandable, because in this case we have a totally spin neutral current. But the ferromagnetic sublattices are well separated. So if we can consider this Taylor junctions or some other devices as a parallel connected as a ferromagnetic layer, and if the effects in each ferromagnetic layer is robust against the disorder, and the effects will be robust in the total. I don't know if this answers your question.
So I think the situation seems clear in the case of an ultramagnet like ruthenium oxide, where you have filtering by K vector, right? So your bands are spin polarized. So roughness at the interface may not fully mix them, but if you have the case like in the last example that you showed, where the bands are not spin polarized, right? Then the matching by different sublattices. So then if you have roughness of the kind that randomizes the matching between the two sublattices, right? Then the effect would be destroyed. So you need to have sublattice A on one side to be matched to sublattice A on the other side for that.
Exactly. But we cannot, because this is clear near material dependent property. We can only say if we have in bulk we have the A distance is much larger than AB distance, then the intra-sublattice hopping is always large. And if we have a very good symbol quality, which do not influence the location of the sets between the two sides of the Taylor junction, then this will not matter.
Okay, thank you. So I think there was another question in chat. Give me a second. So
Alexa
question
was still asking question.
What happens when the changes happen sharply?
So I think we've discussed that. So Alexa, if you want to ask further, maybe you can do that. You can ask the question yourself, but I'm going to read a previous question first. So the question is about the TMR in the manganese gallium nitride STO tunnel junctions. So here the enhanced TMR is due to some kind of good momentum match between the ferromagnet and barrier. I guess of a similar kind to the iron MgO. How can you find that combination? Is there a good way to look for those? Can we find this kind of good barrier material for ruthenium oxide? So I guess, well, suppose you have a bunch of materials and you wanted to do some quick high throughput search. How would you go about it?
Yeah, so this is a very good question. So for what as far as we can answer is in the antiferromagnetic material, because the magnetization is usually compensated by some crystal symmetry. So within some invariant plane or in that invariant line or points, the spin polarization will be zero, or will be very, or at least some spin component will be zero. So this invariant line and points are usually cross the gamma point, which means the spin polarized conduction channels may be far away from the zoo center. In this case, the widely used MgO may be not suitable, because in MgO, the low decay rate area is located exactly around the gamma point at the center. So in this case, we should find some additional other types of the tunneling barrier, which can support the low decay rate area, have the anisotropic distribution like I showed here. But to choose a specific material, we probably first we need to find a specific antiferromagnetic electrode and do some simple calculation like what we showed here. And then we can check, for example, here we find this cross pattern, and then we can look at the widely used tunneling barriers to analyze at least from the symmetry, from the band structure. For example, titanium oxide have, titanium oxide has, in titanium oxide, the CBM is contributed by the d orbitals of the titanium. And so it will have some flat band error in this directions in the CBM, which can generate these errors. So in this case, my answer to this question, to first half of these questions, we should first choose antiferromagnetic electrode and find indeed they have a sizable spin polarization of the conducting channel in the 2D branding zone. And based on this distribution, we then look at the tunneling barriers. By the simple DFT calculation, we can get this. I don't have a direct answer to what is the best area. Well, I think the matching is specific. This may match this material, but will not match other material. But in the second half, which will be tricky, because as Kirill said, we need to have because we have this Néel spin current, which means if the current generated from here followed cross a barrier, if the we need this current started from here injected to the same sublattice in the red electrode. In this case, I think the titanium oxide is the best, because the structure is exactly the same. The sublattice, the lattice mismatch is very small, so we can have a very good epitaxial structure to preserve the position of the sublattices in the two sides of the antiferromagnetic tunnel junction. If you use some other tunneling barrier without the Rotel type structure, which may lead to some mismatch of the positions of the atomic position of the two electrodes, which may weaken the effects, I think. And so far, at least for titanium oxide, we have a predict our 500% TMR, which is quite sizable. I think titanium oxide is so at least for currently, I think it is a suitable tunneling barrier.
So perhaps it might be a good idea to try to create a sort of a database of barriers.
Yes, yes.
Focusing on non-trivial behavior with complex band structure
Yes,
in the
yes,
Berlin zone. So
yes.
materials that don't have just a Gaussian maximum at the gamma point,
Yes.
but have something more complicated.
Yes, yes.
Okay. Other questions, please? Zoom or Twitch, please raise your hand. Doesn't look like it. Maybe let me ask one more question. So you discussed the relation of the anomalous Hall effect and the spin Hall effect in some contexts, in terms of the anomalous current being spin polarized and generating the spin Hall effect. But I don't think there's a direct relation between those, right? The spin current is not just the spin polarization times the charge current. I think this was discussed in the context of the spin anomalous Hall effect in the ferromagnets by Vivek Amin and Mark Stiles in their papers. So if you have those effects allowed by symmetry, right, you can have both currents, but they're not simply proportional through the spin polarization. Is it the same situation here with the tunneling effects?
I'm not sure I fully understand your question, but our starting point is to find some interesting property driven by not only the TMR, driven by the spin neutral current. And when we find this picture, I find this is very straightforward. And we can see if there have only one spin up electrons here and a spin down, only one spin down electron here, we do not have a net transverse Hall current. And if we check the tensors, conductivity tensors for anomalous Hall effect and for spin Hall effect, we can find in conventional ferromagnetic metal, the transverse Hall, the tensor elements for anomalous Hall effect will have in that position, for example, sigma xy, and we also have some tensor elements for sigma xy with some z with some spin component in the spin Hall conductivity tensor. So we think that is quite common for at least for conventional ferromagnetic materials.
No, yeah, for sure. I mean, the symmetry conditions are the same for those. It's just that quantitatively, you can't say that the spin response is simply proportional to the charge response times some polarization. So the calculations show that this is not the case. They're given by different integrals, and they are integrated over the Brillouin zone, so they're weighted differently. So they're not just proportional through one factor. And you could have one of them accidentally vanish, for example, but the other be still finite.
Yes. But at least for some modification, if we have in the transport direction, we have both the charge current and the spin current. We can simply define, for example, spin polarization or spin Hall angles or something else just by spin current over the charge current. So that is just qualitatively to discuss this.
Yeah, I agree. Okay, so if there are no further questions, last call for that. Please raise your hand if you have one. So if not, let's thank Ning Fu again